So welcome. Nice to see you all again. We're back to normal for the rest of the term. Thank you for your understanding as we've been remote for the last chunk of time. So my intention, just before we get into the exam, is on Friday, we'll talk about 15.3 and sort of wrap up that section, this polar section. It would be helpful to hopefully you've already kind of peeked at those videos, but I do have a couple 15.3 videos I already posted before I was gone. But we'll do several examples from 15.3 and the 15.3 homework, which will complete the double integral picture. That does mean that is 15.3 on the exam? No. So no polar or 15.3 on the exam. So I made that decision for a few different reasons. But ultimately that simplifies what we have to worry about immediately. Okay, so Friday will be 15.3. And then when we meet on Monday, the rest of the term will be about this completely separate topic, this Taylor series, which is pretty interesting. The homework, I think, takes people less time. So that's a positive, but there's things to think about. So just know that there's this kind of separate topic. You kind of get a fresh start on Monday. And the final will focus mostly on that. I'll give you some guidance on the final as that gets closer. So anyways, that's the plan. So anyway, that's where we're at. Your job is to get ready for this exam tomorrow. Thank you for all of you that have been asking questions on the discussion board and helping each other out. This exam's really about surfaces. I am going to have a question at the beginning that has to do with sort of wrapping up what we did in chapter 13. And then most of the rest of the exam is going to be about partial derivatives and critical points and a bit of double integrals. So I thought I just, I have these, anybody that just came in, I handed out this review sheet. It's the same one that's on my website. But just before class, I wrote this up. Because when I was a student, this was always helpful to me, for me to put everything on one page and just look at it. I was going to write this up and talk about it with you, but I thought I would just put it up now. So back when we were doing acceleration, there's not a lot I can ask you there, but I could ask you to compute a couple things. Take it to a normal component of acceleration, or going from acceleration to velocity position. I think in one of our review sessions, we did a few of those. But there's quite a few of those in my old exams. If you're trying to look for practice. Oh, sorry about that. I'll try to stay close by. Let me grab one thing here. So first, for everybody, this is where the exam archive is. I can put it in the chat here for a moment. This is where we're working. I do have these things that comment, because some quarters we include 13.4 on the first exam, some we don't. And so I have these places where I've commented where you can see 13.4 questions. Okay. Almost every exam has a polar question, so you will need to skip that. But that's usually fairly easy to spot. If you're using these old videos, these are a bunch of short videos on the topics, you could skip this one. Okay, so that's our primary place to be working. Sorry, Abby, I'll try to stick close by. I don't know exactly what I said there, but okay. So let's take a look and see. So then we got into surfaces, and that's mostly what we've been doing. We practiced a lot with partial derivatives. We did a few general things to kind of get us ready for surfaces. And then we played the partial derivative game a lot in 14.3. That included all sorts of kind of messy partial derivatives so that we could get better at it, including some problems where you had the product rule or the quotient rule or the chain rule, even a few where it was implicit. So I'll have some more involved partial derivative probably here on your test, just not hiding too much here. So you'll have to execute your partial derivative skills. Okay, so then we used them to find tangent planes, and we sometimes think of those as linear approximations. I guess I can add that here since I didn't color code this. But the linear approximation is just another way to think of what that z is. So sometimes we call it a linear approximation. If we want to get really fancy, we call it L of xy. And we move all this to the other side. So a question that asks for the linear approximation or the tangent plane is actually asking for the same thing, just written in a different way. But that's helpful. This sort of justifies the fact that we can just look at the slope in the x and y direction, and that's enough to figure out the tangent plane that just touches. And then we use that in the next section. So we say, well, if we want to be at the top or bottom of a mountain, we want the tangent plane to be like this, which means we want the slope to be 0 in both these directions. And we did several things there. So this requires, in terms of solving, there's a little bit of a skill here. Solving a system of equations in an organized way. I suggested this kind of tree method. The good part is that's one thing. I've had a couple of people message me on how I check my work. I mentioned at one point a way you could check your first partial derivatives. Does anybody remember that? How could you check your first partials? Yeah, you can take the second partials. Take the two mixed partials, and if these are different, something went wrong. So take y and then do x, take x and then do y. And if those are different, you probably messed up your first partials. So that's one checkable thing. Another checkable thing is here. The moment you're done finding your critical points, if you get like x equals 1 and y equals 2, you can know if you've made a mistake. How can you check those? You can shove them back in here. Both of those things I just mentioned are fairly quick checks. So you wouldn't want to include a critical point that doesn't work. It's got to make both 0. Okay, but if you follow sort of the logical process we've been talking about to solve, that won't happen. But then we talked about classifying. And we were just kind of doing that in the last hour. And then we talked a little bit about applied max and min and global max, and we did a couple questions on applied max and min. And I've given a very strong hint about what will be on the exam here. Okay, then we have double integrals. And hopefully we can do some of that today, because there's going to be some of that here. And the part we don't have is the polar, which gives us a third option for setting things up. This is not really this is just saying, first we did rectangular regions, and then we talked about general regions in terms of x or in terms of y. Okay. So that's kind of a recap. I don't know if that sort of review, just a little different style. I'm always trying different things here. But any questions now, general logistical questions or specific old exam questions, I would be happy with any of those. Let me see what's going on here. Yeah, Riemann sums is more kind of a foundational piece here. But yes, I think based off of my hints I've mentioned, I won't be asking directly about that. You can use that to sort of check your work. So let's say you wanted to check your double integral to see if it's reasonable. You could estimate the volume using like one Riemann sum box. Sometimes that's helpful. Some of the things that aren't explicitly mentioned as being on the test might help you check or reason out what's going on. Okay. Sorry about that for everybody in here. All right, so what would we like to do? Particular old exam questions or topic? Yeah, please.
So, like, are those always just like 0 to 2 or 5?
Absolutely. So these are always numbers. If a variable appears in the outer bound, something has gone terribly wrong. So that's a good check on your work. The final answer should be a number. And so if you think about when you're getting to the very end of integrating a double integral and you have something like this, 0 to x squared, something has gone really wrong. Because after you're done integrating, you're going to plug in this x squared, you're not going to get a number. So if there's a variable in the outer bound, something, like I said, has gone terribly wrong. So to that point, I have seen this over the years, and I hope we've made this clear. Let me see if I can think of an example. And let's say this is this. And we have this. I have seen over the years that probably about 5% of students, the question will say reverse the order, and they'll write this, which would be lovely if it was that short. But this is not the same. A reverse the order question is really asking you, can you understand the region that's being given here? So it's really a draw the picture question. What is that region? I hope I gave one that is a region. So I need everything where x is between 0 and 2, and y is between the following two functions. And that's how I think about these. I think about these as tick marks. I think about these as the functions, the bounding functions. So this is the picture I would draw. Then if your goal is to reverse the order, you're trying to relabel in terms of y. So let's just do that real quick because this is a fairly quick question. So go ahead and take a moment and think about what the new labels would be. So draw the region, new labels. There are two questions. There's new tick marks, the y tick marks. And I need to give the functions in terms of y. So what's the biggest and smallest y can be? Tick marks are 0 to wherever in the world that is. So what are those? And you, oh yes, somebody in the chat's is giving me the bounds here. And you can really do those separately, but the tick marks are 0 to wherever this is. And since the x is 2, the y has to be 4. Okay, so it's 0 to 4. And then the inner bounds need to be, if I start walking, where do I hit my region and where do I exit? So we're mowing the lawn in a different way. I need to give those bounds. So I need to give the right bound, which is something, and I need to give the left bound, which is something. One of those bounds is a constant. The right bound is. That's x equals 2. So that means the upper bound for x. We have trouble thinking in terms of left and right, I find. We're used to work thinking in terms of up and down. But if you go this way, it's bigger. Sometimes in class, I even stop and I'll give a couple points like 3, 1, and 7, 1. And I ask students how far apart are those? It's kind of a silly warm up. How far apart are those? 4. Did you do right minus left or left minus right? You're right minus left, right? We tend to not think that way. I feel like if I draw 2 points this way, we sort of know immediately. We're just used to thinking horizontally. I don't know, maybe I'm wrong. That people would know this is 8 without thinking, but have to think for maybe half a second longer that that's 4. Anyways, bigger is to the right, so this is bigger. That means this is a 2. The other side I need to figure out, if I hand you a y, what's x? So you get x is the square root of y. If you solve, you actually get plus or minus, but minus is on the other side here. Okay. So the question is really saying, can we draw the region and relabel it? That's what a reverse the order is about. But that wasn't your question. Notice in both of them, the constant's on the outside. So that was the point there. Good, good. What else can we do? Yeah, please. Yeah, let's take a look. I should reprint the homework because I think I have a different thing. So what's 11 about? Okay, enclosed by what? There's one that has to do with volume bounded by the plane. Let me look at your number 12 here. Consider the region. Let me draw this. Find the volume of the solid bounded by the cylinder, the plane, this other plane, and this other plane, and in the first octant. It's a long list of equations here. Bless you. So we have x squared plus y squared is 16. We have y is equal to 2z. And if you've caught on, the first thing I'm looking for are my z's. And then I also have x equals 0, and I also have z equals 0, and it says first octant, so that also means all of these are greater than or equal to 0. That's a lot of stuff to decipher. And then we've got this tool that finds the volume from a region to a surface. So that tool says, you find a region on the ground, you find a surface, you plop the surface in here, you describe the region, and this will give the volume between them. Okay, so these problems are about using this tool to answer this question. So step one is to figure out, is there anything that describes height here? And if you take the next course, Math 224, we add an extra first step, which is to decide what we want our output variable to be. Like you could say, well, why don't we want it to be y or z or x? That's for the next course. So for this course, we tell you that everything we give you can be done in terms of z. But the truth is there's like 6 ways to set this up, because you can do it in terms of z and then use x or y. You can do it in terms of x and then use y or z. So there's lots of, there's even more options. But in this course, we're just focusing on what if z is the output. So step one is to find your z. And there's only one thing giving me height here. It's right here. So I'm going to do some challenging solving. Z is a half y. Maybe that wasn't so bad. That's what's going to go here. That's like my flying carpet. Okay, so I've decided that I'm going to do everything with z as my output variable. Now I have to remember when I use that tool, it finds the volume to the xy plane. But that's good because the question wanted the volume to the xy plane. So we've taken care of that. So I have my flying carpet, I have my surface. What do I need now? I need the other thing that goes into this tool. I need the region. So what in the world is that region? So now I do this. So I've kind of been programming you to do these two things. Find your z's, that's your integrand. Draw your region. Okay, we're going to need to draw all the other constraints we have here, which I think are these. So I need to draw the region where x is greater than or equal to 0 and y is greater than or equal to 0, and I'm inside that cylinder. Okay, so I'm going to draw all those. I'm going to draw a circle of radius 4. And I'm going to stop right there because we're talking about the first quadrant. So that was the importance of this first quadrant piece. And I think I could even draw this if I had to, because anybody know what z equals 1/2 y looks like? You don't need to do this for the problem, but what is z equals 1/2 y? In 2D, it looks like a line, but in 3D, what is it? It's a plane. In fact, you could even draw this thing. You could say, here's x, here's y, here's z, here's the line, z equals 1/2 y, and then extend it out indefinitely. That's that plane. It's a line cylinder, but we don't call it a line cylinder. Call it a plane. And then I've got this region on the ground, which I'll try to draw here. Circle of radius 4. And we're finding the volume between them. So it's like it's part of actually, I know the name of this. It's part of an ungula, since I've been studying shapes so much. It's half of an ungula. Ungula means horse's hoof. But it's like what happens when you take a cylinder and slice a part of it off. Anyways, that's the thing we're trying to find. You don't have to visualize it at all to do the problem. But I just wanted to emphasize, we have a region on the ground, we have a surface. And those things we could sort of find automatically. Okay, any question on that setup piece? That's pretty much how all the chapter 15 problems start. I sometimes call this step 1 and step 2. Step 3 is the interesting thing, and the reason we have several sections in chapter 15, which is turning this into bounds. So you can do it in terms of x, or you can do it in terms of y, and the best way to do it, we don't know yet. The best way to do this problem is to use 15.3. But this can be done. This was in 15.2. Okay, so if you do it in terms of x, you're going to label this x. You're going to ask yourself what the biggest and smallest x can be. And then you're going to give your functions. So this would be the top bottom approach. So let's look at our region and label it in terms of x. What's the biggest and smallest x can be? 0 and 4. Those are our tick marks, so to speak. And now I'm going to mow the lawn. So now I'm going to walk from here to the edge, and I'm going to find the pattern for those two things. What is this y? And what is this y? One of them's a constant, but the other one's a curve. So it's one other thing I could fill in without thinking. The bottom or the top is a number. Which one of those is a constant? The bottom. So I can fill it in right away. So now I need to do the top. I need to know based off of x how far it is from here to here, given the fact that this is a point on this circle, which was x squared plus y squared is 16. So I need to be able to hand you an x, and you need to be able to give me the formula for the positive y you get. So we need to solve for y. Y squared is 16 minus x squared. Y is equal to plus or minus the square root of 16 minus x squared. But we want the positive one. That goes here. So that will give us that volume. There's a separate issue, which is to integrate. But how are we on the setup? Yeah. This one, it's almost identical if you did it in terms of y because of the symmetry of the region. If you did it in terms of y, it's going to be 0 to 4 and 0 to the square root of 16 minus y squared. I think this one works out okay because the first step of integration really simplifies things. And what I mean by that is if we go one step in, it looks like the integral from 0 to 4 of 1/4 y squared. And we're in business because when we substitute this in, the square root goes away. If you change this function to almost anything else, this will not be nice to do in terms of x or y. So just a comment, this is for Friday, but the best way to do this problem is to do it in terms of polar. We would say the angle is between 0 and pi over 2, and the distance from the origin is between 0 and 4. This is another way to describe this region. And you'll notice that that has all constants. So those bounds are way better, but it requires we change everything else. So that's the third sort of tenet, the third option. That won't be on our test, but just so you can see, the third option for this would be 0 to pi over 2, 0 to 4. We'd replace the y by what is equivalent in polar, which is r sine of theta. And then we would talk like a pirate, r already theta. So that's what we talk about in that section. So that's a nice little preview of 15.3. It's this third option, which is very good when you're dealing with circular regions. And since circular regions are come up quite a bit when we're measuring things, it's nice to have this polar option. Just gives one more approach. Okay, that's 15.3. So we'll do some of those on Friday. In this case, all three of these would give you the same value. All right. And that does mean, like on a test, if you're checking your work and you have extra time, sometimes that means you could compute it in two different ways and see if you get the same value. Sometimes it's not as easy to do. Lovely. So that's a good little game. Other questions on this one? Looking in a few different places. Oh, you had another one you were asking about. This one? This one. Draw, erase. You might have had different numbers. So this is a 15.2 homework. So this question is about drawing this region. And we should think about this as tick marks. And these as our functions or our bounds. So in general, when I'm doing a problem like this, let me make this a little bigger. I would say, okay, and I always have to, in my head, take a moment and line these up. But the tick marks, the starting and ending of my pattern, are 0 to 64. And then they're giving me a pattern based off of y. That's telling me how far to walk to get to my region. And they gave me these two formulas. So anytime it's dx dy, you can think of it this way. What will change is the functions that are the bounds. They find a pattern based off of y for those inner bounds. But what this really means, what I used to tell students is you can ignore everything else about the problem. If this is helpful, I'll give you my old advice, which is immediately start graphing the inner bounds. In this case, that would be x equals 4 and x equals the cube root of y. If you can graph both of those, you probably will have the right picture. But it's good to also check the tick marks. Okay, and an added tip is if you get an equation that looks funny to you, write it the other way because you're going to do that anyways. So I would immediately take this and write what? Y equals x cubed. So the truth is, if I saw this question, those would be my very first thoughts, whether I write them or not, is I need x equals 2 to be the bigger bound, x equals 4, and I need this to be the smaller bound. So now it comes down to correctly drawing x equals 4. I have seen some mistakes on that sometimes. People don't guess. A bad technique is to say it's either a vertical or horizontal line and flip a coin. And if it's heads, do vertical. And if it's tails, do horizontal. A better technique is to think about conditions. So you start to think about what are the points where x is 4 and y can be anything you want. You plot those points and connect them. So it's this line right here. That's x equals 4. Okay, and then the other one, it's also helpful to realize it should have been on the right. It should be the bigger. So there's a few different signs. We do have to remember a cubic. But in my head, that's my picture of a cubic in my mind. But I only need the stuff that's above 0. So let's graph that. So we're coming up, we're swooping, we're going this way. Now I'm a little worried. What happens when I plug in 4? Is it 64? It's 4 cubed. I'm guessing it's 64. I just am kind of doing a quick check. Okay, that was really the job. There's a couple little things I'll say here. It's very easy to draw a line here. The moment you extend this tick mark out further, then you're confused, or I'm confused, because then I don't know which region it is, this region or this region. So that's why about 5 years ago, I started to say tick marks to try to emphasize, don't draw a line there. Because if you just blindly draw a line, you're going to get confused here. But you can also see that the ultimate thing, the ultimate piece, is that as you walk out, the first thing you should encounter is this function. The last thing you should encounter is the 4. And surprisingly, we're just describing a region. And luckily that works everywhere in between. Okay, none of that is what we wanted. With practice, you can generate that picture very quickly, but I just have noticed that some of the things I just said are often the points of confusion. Is that all right? That's your main job here. You put all your energy into making this picture. Because if you can make that picture, then you're done. What do I mean by that? So now we're going to switch gears and say, what if I labeled this in terms of x? And I'm going to ask, what is the biggest and smallest x can be? That's going to be 0 to 4. And then based off of x, what's the biggest and smallest y can be? So I need these bounds. To me, this feels a lot like Math 125. Just in Math 125, you were subtracting these. Now you're using them for bounds. Okay, so write down what you think goes in that spot. So the lower bound is 0. And the upper bound is, I don't know, I erased it unfortunately, but it's this equation, but I need to be able to give it an x. So it's x cubed. And these are completely the same. So writing these bounds here is completely the same as writing these bounds here. And in general, the connection is the region. Sometimes you can, like, this gives you the wrong, you might be able to say, well, I think I could guess that. But there's just enough variation that if you don't draw the picture, you're going to get the wrong side. You might get lucky sometimes, but okay. So the reason I had you do this was one of these is much easier to integrate than the other. Ooh, I miscopied, didn't I? This is much easier to integrate, but not what the question asked. The thing we're trying to integrate is e to the x to the fourth. Did I? Oh, I made multiple mistakes. None of these were on purpose. What's my other mistake? Yeah, these don't make sense. There's a few things that flew me in on this. One is I didn't change anything. The other is I have an x escaping a dx. Something's wrong. So when I looked up, I realized I'd made a mistake. Okay, so variables can't escape. And then you can line up again in your head. Okay, those are 0 to 4, good. So this is easier to integrate because there are no x's here. I mean, there are no y, sorry. So this one you're just stuck forever, can't be done. This one you can immediately start working. It's still a made up problem though. And the reason we can do that integral is because it leads to substitution. But we've talked about the drawing the region. That's the main skill there. You can definitely do some of the integration as well, but questions on that one? It's all about turning the region into a picture. The bounds into a region. Lexi, any other questions on this one? Yeah, let's take a look here a little further. So this now switches gears to just for my space. So when I plug in an x cubed, that's just going to be an x cubed. This is going to be a 0. Let's rearrange it in a more pleasing way. So we're going to do 6x cubed ex to the fourth. And I always say that I think this is the hardest integration method because you have to see two things, but this really should jump out at us that we have a x to the fourth on the inside and an x cubed on the outside, which means we're going to engage our substitution muscles here. If you really want to be good with substitution, you learn to change everything but the squiggle, but the integral sign. So there's our substitution. The reason it works is because of something we're going to see on the outside. So let's play the game. Du is 4x to the third dx. I think when I was a student, my instructor made me try to turn the 6 into a 4 by rearranging, which is perfectly fine. I have found that more students like it when I do this. I'm rearranging. So I'm going to put this here, 1 over 4x cubed du. And then I'm crossing my fingers. Did all the x's go away? Yes. Okay, so it's a successful substitution. That's something we had to see happening back at the beginning. That's why I think this is the hardest method, because you have to see ahead. All the other integration methods don't require you to see ahead. Okay, let's go. And then what are the bounds? Yeah, please. So at this moment, I'm not integrating yet. It's a rewriting. So I'm rewriting the function in a different way to strip away the chain rule. So what I mean by that is this. So this is more of a theory of integration by parts. But if I did the derivative of ex to the fourth, what would you get? So this is the chain rule just for a moment. You would get ex to the fourth times 4x cubed. So that's the chain rule in all its glory. Now what happens if I erase this and ask you to go in reverse? That's what we're doing when we're doing substitution. And we have to realize that two different things happened. We had an E change, and then this stuff that's happening here is just stuff that's on the inside. So it really was two separate derivatives. So if somebody told you that, then you could say, well, where did this come from? This came from e to the u. Where did this come from? This came from x to the fourth. And so we're trying to split up our thinking. And so substitution helps us get rid of the piece that we know came from this chain rule. Okay, so it's a rewriting. So that's what's happening here. And because we're rewriting, we're actually transforming the entire problem. So we can, if you really want to make your life simple, you change the bounds as well. So when x is 0, this becomes 0 to the fourth, which is 0. This becomes 4 to the fourth. Holy cow. 4 to the fourth is 16 squared. Is it 256? I don't trust myself there. I'd have to use my fingers. I think it's 256. 16 and then double 32, 64, 128. Okay, 256, I hope. So anyways, the point of this is this technique doesn't solve the problem. It just strips away the part that has to do with substitution. And says, if you don't like that problem, do this problem instead. I do like that problem better, except for the 256. The funny thing about Math 125 is you never learn new integrals. You get these 10 integrals pretty much at the beginning, and then every other technique is to try to massage something into one of those 10. So every technique involves crossing your fingers and hoping that you can get it into one of the 10 or so things we know, but this is a good example of that. All right, what else can we do? Let me look, kind of regroup and see where we were at. We're in week 7. How did I lose my way? There we go. So I feel like we now have hit quite a few things here. We did a volume, a setup of a volume. We did some sort of first order. We did a little bit of computing. All right, what else would we like to do? Our time, I'm making sure there's no chats there. I guess I can see it up here, but then they can't hear. What else do we want to see? Or general questions. Does anybody have, I know some of you have exams in other courses. Does anybody have an exam in another course? Yeah. Oh, you have a question? Yeah, go ahead. Yeah. Compute the tangential and normal component of acceleration.
It's like the one with the
Yeah, let's take a look. I hope that I copied them all down. Number 10 is kind of a long problem. I would have to really clean it up to make it appropriate for an exam. I assigned it more as kind of, I think it's kind of an interesting example. The part that we can take away from it is the integration piece. So if I say that the acceleration is 0, negative 9.8, let's say. This is a 2D version. A 3D would look very similar. So let's say we have an object that's only being acted on by gravity. That sounds too physicsy. Let's just say this is what your constant acceleration is. And then someone gives you some initial conditions. So that part I could ask about. it depends on what we want our initial conditions to be. So let's pretend that our initial conditions, how about we're 6 feet tall? Nope, it can't be feet because we're in metric. We're 2 meters tall. And we have some initial velocity. And we're going to throw this thing up in the air, this heavy rock. We're going to hit our math professor. Okay, let's go. So let's do this. So you would need to give your initial position. So your initial position is 0, 2. And the initial velocity, let's say I just give it, is 1, 3. Over 1 up 3. Okay. So I wouldn't say it in the form of projectiles, but if we now solve, what happens? So the acceleration is the second derivative. So this is r double prime. So you integrate and put in your initial conditions. This one is, I mean, the bad part about this in terms of a test question is that some students already know the answer from their physics course. Some students will raise their hand during the test and would say, can I use the kinematic equations? These are the questions I usually get, but let's just focus on the calculus for a second. So if we integrate 0, what do you get? We're not used to integrating 0. It's actually not 0. What is it? It's a constant, yeah. I don't know what that constant is yet. And then you'd have 9.8 t plus a constant. How do you find those constants? You put in your initial conditions. We use the fact that I said the initial velocity. When I plug in 0, I get a 1 and a 3. Now, in this case, when I plug in 0, I just get the constants. So that means the constants are 1 and 3. 1, negative 9.8 t plus 3. Then you integrate again. So the question kind of was confusing in how it was stated, but this is really what it was about. Negative 4.9 t squared. And if you've done projectile motion, you see that 4.9 popping up a lot. Actually, I've been told that in a lot of physics and science classes, you're told to just use 10 for gravity to keep things simpler. So I might be wrong. Maybe 4.9 isn't popping up anymore. When you plug in 0, you get 0 and 2. So this would be an accurate model, ignoring air resistance, for someone 2 meters tall throwing it with that velocity. That velocity is pretty small, so it's probably like this. That would be an accurate model for that. The 3D version is the same thing. The hard part about these problems is we just can't ask that interesting of questions that apply to situations because forces tend to depend on where you are. But that's that idea. So that was the intended idea of the problem. The reason it kind of got complicated is they were playing around with your initial conditions. They were playing around with what could be here based off of the angle. So that's why that was confusing, the confusion of the problem. So anyways, that's one type of thing I can ask about acceleration is integrate, plug in your initial conditions. Good. Other questions? Yes. Mm-hmm. Yeah. Let's take a peek. So I think it'd be fun to just make a question. So here we go. Here's a question that says the minimum distance from a point to a plane. This question says the minimum distance from a point to a cone. And this one says the minimum distance from a point to some random thing here. Let's do our own problem. So here's what I would like. I'm going to make one up. So let's pick one of our favorite surfaces. And this might, in doing this, I'll probably gives something that's not solvable. But here's an interesting surface. Actually, let's just do this surface. X squared plus y squared minus z squared equals 1. What is that surface? It's hyperbola to one sheet. Okay, let's stand over here somewhere. And let's say we want to find the point that's closest to us. And you could actually do this in general, even. It could be a really messy point. The solving might end up being sort of bad. So let's pick a point that's on the XY plane. So how about the point 1, 2, 0? And I would like to figure out the point that's closest. Okay, so now here's my question. Find the point on here, and there's more than one, on here, that is closest to 1, 2, 0. On here, that's what I said in words. Okay, that's sort of an interesting question and the reason I think there's two is if you looked at it from the side, I think you could walk up here and I could walk up here. I'm a little worried that the closest point might be right here in the middle, in which case this point, well, question won't be as interesting. Okay, so we are trying to minimize distance. The distance from this point to this point. So minimum distance questions, minimum from a distance to a point, if you're using calculus to solve it, all kind of start the same way. You have these points X, Y, and Z that you're only allowed to stand in these certain places, and you have this other fixed point. I mean, even more interesting would be like, what's the minimum distance between two surfaces? But that starts to get more complicated. So I'm trying to minimize that, this distance. Okay, but that has three variables in it. And you know, if you look at the question, it doesn't even make sense yet. So if I said, what's the minimum distance and you're allowed to stand anywhere, where would you stand? So if I said, here's this point 1, 2, 0. And I said, I'll give $100 to whoever can get closest. You all would jump up and go where? On top of this point. Okay. So this question is saying you're not allowed to do that. Why am I not allowed to stand right on there? Because the points have to come from the hyperboloid. So that's what the question's asked. That's why it's kind of interesting. You have to stand on the hyperboloid and like reach and get as close as you can. You know, if I said, what is the point on this table that's closest, maybe it's here. Table with a plane, and you'd be able to get closer. Okay, so this is a very general type of question, whether it's interesting or not. Okay, so we need to somehow get this into here, this restriction. Can I do it? So you can either get rid of X, or you can get rid of Y, or you can get rid of Z, but we'd like to get it down to two variables and basically get a formula for the distance based off of X and Y. So I think I'm going to get rid of Z, and we're about to find out if this example I made, it was any good. Okay, so solving for Z, I would get X squared plus Y squared minus 1 is Z squared. So that's the connection between, if I pick a random X and Y and then compute the point on the hyperboloid, this would be the relationship. So now I can give the distance with the restriction in there. And then from here on out, that's the function I'm going to study. And I would like to know the smallest that can be. The smallest that, if I'm trying to study something and find when it's smallest, I'm going to want to find the critical points. And generally, you have to think about critical points and boundary points, but look, we'll see. Let's go. So there's a separate, so any question about the setup. So pretty much every minimum distance question, like, I don't know if this would be helpful. Sometimes I do this. Let's say you were trying to present a general paper on something like this, and you said, you give me a flying carpet, I hand you a point, x0, y0, z0. Give me the algorithm we just described. So you would write down, we want to minimize the distance. The distance would be the square root of, let's call this, we'll leave it, x minus x0 squared, y minus y0 squared, z minus z0 squared. And then you would do what? If you're giving someone a general layout, you substitute and you get this function. So this is the sort of stuff I do when I'm making like general animations. I solve it in general. And then I try to think of cool surfaces that have this answer. So I think I could even go further and write down what the parcels look like. Write down a condition for a minimum. That's like a bigger project for somebody. But anyways, for this problem, what I need back here is the partial with respect to x and the partial with respect to y. And I need to know when both of them are 0. The textbook and pretty much anybody who does this, if you search online for this, they always square it because the square root is an increasing function. I often say that that's not essential to the problem because the square root, I like that. You can definitely do that. But the derivative of a square root is 1 over 2 times the square root times the derivative of the inside. So sometimes I just write 1 over 2 times the square root of the mess times the derivative of the inside. And the reason I don't care about that is because I'm about to set it equal to 0. So anyways, now I need the derivative of the inside. So this would be 2x minus 1 plus 2x. This would be 2y minus 2 plus 2y. And then I can solve this for x, solve this for y. This gives me x is something, a half, maybe. This gives me y is 1. I'd have to think a little bit more because I haven't done this problem carefully, whether that doesn't be, but that's the only critical point. A lot of times in a problem like this, the reason there are 2 answers, why would there be 2 possible answers here? It has nothing to do with solving for critical points. It has to do with when you plug it back in here and solve for z, you get a plus or minus. Did I sort of hit your question? Yeah. Okay, so it's an optimization that sort of fairly directly lends itself to finding critical points. And it's a problem where generally we can usually think about it and say, okay, there's got to be an answer to this. So it's less having to justify. It's 11:50. If anybody has to go, I'll maybe do one more problem. I'll turn off the recording at noon, but I also will stay after that and chat with anybody that wants to talk off camera. So anybody on the Zoom have another question? in normal, if there's anything wrong with the time I've assigned to you for your exam, send me a message. But I'll be there at 8:30, proctoring for everyone that's taking it at 8:30, and then you'll do your normal thing tomorrow. But I would advise you to come on Friday, and we'll do some 15.3. Thank you, thank you. There's no question on here. There was a hand in the back. Maybe they stepped out. Is there a particular one we want to look at? I'll put this back up. Oh, there's a question on here. Spring 19, number 3B. Yeah, so this is a polar question. So you can ignore this this would be something to practice for the final. I'm going to ask something polar on the final. But this one you might actually could do this. Yeah, we could do this in terms of X. Okay, but it's a challenge. The reason, so I would not want to do it in terms of Y. It could be done in terms of X, but you would have to solve for what these are. One of them isn't so bad. This is Y equals the square root of 1 minus X squared. But the other one, actually, it's not terrible. Y squared is X minus X. Yeah, thanks for coming. This would be, so it is possible to set this up. This is 0. This is 1. Oh, I could do this in Cartesian. It would be 0 to 1. So I was wrong. X minus X squared. 1 minus X squared. So this would be a correct setup for this thing they're asking. Now, the bad news is that's not going to be a very nice integral. So again, I wouldn't ask this on the test. We could do that. That's about as far as we could go. It's trig substitution, so it's going to be kind of a lot of work, and then you have to integrate again. So while I think it's doable, it's not. But in polar, this is much better. But I'm going to leave that because this requires some of our 15.3 stuff. Yeah, see ya. Thanks for coming. Other questions? Things we want to look at? Anybody in here have a particular one they want to look at? Yes. Yeah, let me think for a second. Yeah, thank you. That's a partial fractions. Are you asking for integration by parts? So, yeah, I think that, let me think for a moment. Okay, so let's say you had to do this integral. I don't know how this is going to pan out here. Y equals X. Let's make this a 2. Let's say you have to do the double integral over this region of cosine of X dA. Okay. We'll see how this goes. So there's two ways to set this up. Maybe we could set up both, and one of them I think will lead to integration by parts. And one of them might not. Let's take a look. So if we do it in terms of x, it's 0 to 2 and 0 to x cosine of x dy dx. So that's one setup. And then the other would be the integral from 0 to 2 y to 2. But the one I want to talk about is this first one. So rather than write that. So let's say you set it up this way, which is a perfectly reasonable way to set it up. And you start integrating. So what's your first step? So integrate with respect to y. Because there's no y here, thanks, Kevin. See it. That's like it's a constant. It's like there's a 5 sitting there. You can even yank it out to make that very explicit. And so if you integrate this, you get 0 to 2 cosine of x, y, evaluated from 0 to x dx, and then you get the integral from 0 to 2 cosine of x times x. So this is how by parts makes appearances. Integration by parts really, I sometimes say it's 5 main examples. There's more things, but the main examples are x times some cosine, x times some sine, x times some exponential function. I'm just thinking of percentages. 80% of the time that I use integration by parts, it's one of those 3. That's by far the most. The next maybe 15% is when there's a log in there and maybe some power of x. 10%. And then we have very special ones. Inverse trig and this one. I don't know, 2% of the time. 5%, 5%. There's my percentages. For the most part, that's it. Products, logs, and inverse trigs. Sometimes you have like an x squared, which means you have to do integration by parts twice. But it's things that are good for those situations. So when you happen upon this and you realize it's not in my table and I can't do it with substitution, it'd have to look like this for it to be something where I could do substitution. That's when you think by parts. So by parts goes like this. It's a rearranging technique that comes from undoing the product rule. So it's this, my very, very brief version. We like to, for some reason, use U and V. But if you think about like what the derivative of a product would be, it's the first times 0 to the second plus the second times 0 to the first. And somebody had the clever idea to write it this way, the product rule, first times 0 to the second plus the second times 0 to the first. And then say, well, if we're trying to undo the product rule, it's going to look like this. But the problem is when someone hands you an integral, they don't hand you both parts of the product rule. They just hand you one. And so then we rearrange this in a form that allows us to sort of move things around. So the rule is this, u v minus the integral of v du. And the real method is to take something hard and replace it with something easier. Okay, so what I like about the method is you don't, you don't have to see very far ahead. It's like you can turn the crank. So here's how I set it up. And I have kind of for me, a way that I think helps me remember it fairly quickly. So the goal is that the integral you're going to get there is going to be easier. And it actually doesn't change your variable at all. And so I often say that there's just one thing to do, and the thing to do is to pick u. And your choices are this or that. Once you make that choice, the rest of it will be like filling in a template. The choice is to make things simpler. There's even, I can make it extremely not have to think, but so a quick answer is we would like things that we know the derivative of, like logs or inverse trig. If those are there, we're going to pick that to be our u because we have to, because there's nothing else that we can do. There's no way we can make progress. If there's a power of x, we're going to pick that as our u. So power of x, I mean like x or x squared. If there's an exponential, if there's a trig. So since these are the main situations where we use this, it turns out you want to pick u to be the thing that's higher. So in this problem, we have, this is the Lipit scale I made up or stole years ago. So this is a power of x. This is a trig. Power of x is higher. That's your u. But the real decision making is, does it make things better? So the moment you make this choice for what is u, everything else that you see there is your dv. And then your job is to take the derivative and take the integral and hope that that's better. So derivative is 1. The integral, and these are the places where it's easy to like get signs wrong. And then I always remember it in terms like as follows. So the formula says put those two things together. So I always remember it as kind of smushing together the main diagonal. So this is going to be x sine of x. And then I smush those two things together. So it's going to be sine of x dx. And that's the end of integration by parts. The rest is, can we then do what's standing? So there's a few little things that happen along the way, but hopefully at that point it's something we can do. So then we say, where did sine come from? It comes from negative cosine. And then we have our answer. Oh, in this case, we had bounds, so I should finish it. I got on sidetrack of talking about this. This is kind of a bad example because you're going to be plugging 2 into sine and cosine. So that's the quick recap.
So it's not like I have a challenging integration by parts problem. The challenge is to realize when suddenly it pops up. And sometimes I may not even have. The problem with these things is you can sometimes set them up in more than one way. So it could be I intended a certain way that doesn't require an integration technique, but if you set it up the other way, it might lead to by parts or substitution. So there won't be any sort of hard by parts, but sometimes it kind of unavoidably appears depending on the path you take. Substitution is something that is somewhat more likely to be there just because it's really hard to avoid. But by parts is it's a little more specialized to these situations. So the real thing is pick your u, dv is everything else, derivative integral, and so I really remember it kind of structurally. I don't even remember the form. I just pick my u, write the dv, derivative integrate, and I put those two together. Yeah. So,
oh, there is so a little comment about evaluation. This is more of like a matter of taste. So you could just integrate like I did here and go all the way down to the end, then plug in a 2 everywhere. And then plug in a 0 everywhere. And that's perfectly fine. Sometimes to like kind of save paper, people will evaluate as they go. So they'll put a little bar here, 0 to 2 and 0 to 2. And what they're effectively doing is rather than wait to the end to compute that part of it, they do it earlier. And especially if the other part of the integral starts to become long, it's kind of nice if you can just turn this into a number right now, rather than wait. But that's more a matter of taste. But normally in a textbook, you would see it written this way of, I evaluate the first part, store it there. I find one of the hardest parts about integration by parts is to not forget this minus. And sometimes people get a minus wrong here. And so there's like a couple places where you can lose a minus. In this case, there's no minus, but the fact that you're doing this quick switch between taking a derivative and integrating makes it sometimes easy to make a mistake there. Powers of X. There's all sorts of acronyms like this. You would pretty much always like U to be X, because when you take the derivative, it gets simpler. Well, if there's so something like this, the problem is, well, first, it's not obvious that by parts is necessarily what we want to do. But the problem is if you put your X here, which is somewhat desirable because then this becomes simpler, you have to put your log here. And then we're just stuck. Like we can't make progress because we're not taking the derivative. So we sort of, for these problems, we're stuck in this sort of this problem of you have to pick this to be U because if this method is going to work, because you have no other choice. And so that's what's true about inverse trig and logs. And the truth is we would never have a problem that has both inverse trig and logs. It's just, so the acronym, you could switch those letters. You could also switch these letters. It wouldn't matter. It's just sort of trying to find a word. Yeah, we would like the powers of X to be our U. But if there's a log or inverse trig, we have to pick the other. Is there a hand in the back?
Yeah. Just curious, note wise, are we in the nature that's not gonna be part of this test, correct? It might just help you visually if you're doing a volume. If somebody says, find the volume of these two things, and you knew one of them was a cone or something, you know, help.
Questions? Yeah.
Can we go over spring 23 question 4?
Yeah, let's look at that. Spring 23. Question 4. And I'm going to erase this because I think I've written all over this a little bit. I think this term I didn't have a problem that had minimum cost. And so I think if I asked this question, I would just change a couple words. I would probably say minimize the surface area. It doesn't change very much here. So just a small comment, because the whole thing costs, I think it's made of plywood and it says it's $3 per square foot. So if you could find the total area of all the plywood and you went up to the cash register to pay for it, they would multiply that times 3 to get how much it costs. So the thing we're minimizing is actually 3 times the surface area. But the 3 is kind of immaterial. I mean, I could change that to some other number and we still would get the same critical point. So let's say we get rid of just for a moment, the $3 per square foot. And I say minimize surface area. Then that looks more like one of our homework questions, except this one has this little barrier in the middle. I think in the homework, you didn't, it was just like it ended up being a cube or something for one of them. But let's say with a goal. So the goal is to do minimum surface area. Or total area. And they're calling this, so they've already labeled it for me. This is X. This is Z. And this is Y. So they say we would like to build this box that has one divider in the middle. And we want the surface area to be as small as possible. And we want the volume to be 6. So for me, the key words there are that we're minimizing surface area. So that's where I would start. So what is the surface area of this box? So we have all of these sides to figure out. So there's 3 of those. And then there's 2 of these, the Y by Z. And then there's the bottom. You don't have to draw these pictures over here. This is just me kind of explaining. So the one initial challenge is we need to give all the surface area based off of these dimensions. And so that's going to be the bottom, which is X times Y. That'd be the area of that part. And then there's going to be 2 of these Y times Z. And then 3 of X, Z. So that was the initial challenge, was to find the total area of all those walls. So now we're going to look for the constraint in the problem. So without a constraint, the question doesn't make any sense because you just wouldn't build it. This would be 0. So the constraint is something that some part of this is forcing us to build this. And it's the fact that they're saying the volume must be 6. So we're hoping we can somehow take that information to give a relationship between X, Y, and Z, and then substitute that in here to get a 2-variable function. So we have to think about what would the total volume of this box be? I think the wall in the middle, imagine the wall in the middle is very thin. It doesn't affect the volume in any way. And we have a box that looks like this. And the volume is X times Y times Z. So this is how these problems typically set up. You have something you're trying to minimize. You have some sort of restriction. What do we do next? Yeah.
So, I remember think it was like the one equation is the other equation.
Mhm.
Reverse it, that's bad. That
that's true. But the surface area to the volume.
Yes, we want the surface area function because we're trying to, the ultimate goal is we're trying to make surface area. This is what we want to minimize. And the strategy is to try to find the derivatives of that. So the surface area with respect to X, the surface area with respect to Y. And so whatever you're trying to minimize, we're trying to find that point on this new thing, this new function where the slopes are both zero. So we're not trying to find when the slopes of the volume are zero. We're trying to find when the slopes of the surface area formula are zero. The other thing is there's actually only one equation. This is an equation, meaning it has variables and numbers on both sides, whereas this is just a named function. So it doesn't even make sense to plug in surface area because it's not equal to anything. That this is actually just a name, as opposed to saying it has to be something. So what we're trying to do is get rid of one of these variables using the fact that there's a connection between all three. So anyway, the next step is to solve for Z and shove it in. So then you get the surface area with just the two variables X and Y is XY plus 2y. And here's where I'm going to substitute this in. So this is the general layout for essentially any minimum surface area question. This one was just different because there were a different number of sides. But I think that will simplify now. So now we have the surface area with the constraint in there. And I'm getting 12 over X and 18 over Y. If we were really stuck, we could go back. This is a weird problem in that you could just do experiments. This would not give you the answer, but you could say, okay, can I think of numbers where the volume would be 6? Well, how about 1, 3, and 2? This formula, if we did it right, tells me the surface area for that. So you could test it out. You could say, I know the surface area of this is of all of this together. And then plug into this formula and make sure you get the same thing. So what we just did is we said, based off of just X and Y alone, you can plug it in here and find the surface area. So for example, if you get 1 and 3, then we could figure out that that had to be 2, and then we could plug in. But I don't want to plug in values. I just want to know which values make this the smallest. And we start that search by looking for the critical points. So I need the derivative with respect to X. I need the derivative with respect to Y. And there's a few little things to say here. So first, I like the way it's written now, but if I'm going to do derivatives, I may want to write it this way. Okay, so let's do the derivative. So derivative with respect to X is going to be Y minus 12X to the negative 2. And the derivative with respect to Y is X minus 18. And I personally would rewrite it without the negative exponent because I think it makes it easier to solve. But that's not necessary. But I need to know when those are both 0. Often these minimum surface area questions have expressions that look like this. So we'll be done if we can combine, but there are some fractions. We have to take a little bit of care. Any questions so far on where we're at? Yeah. So the part that takes a little bit of care here is I need to substitute. They don't look like they easily factor. They kind of look pretty similar. So I think I would just pick equation 1 and write y is 12 over x squared. And then I'm going to substitute that into equation 2. Most often when I've seen errors on the algebra, it happens right here because we're substituting into the bottom of this fraction and we're substituting a fraction into it. I kind of have two thoughts about this. What if we wanted to prevent some of the errors, we could simplify right away, meaning multiply both sides by y squared. So from experience, I might be inclined to do that, but we can also plug it in directly. So minus 18 over, and then plug in what we just got. So I don't like to look at things like that for very long where I have fractions inside of fractions. So this would be the moment. I think if I was doing this, I'd multiply both sides by this. Here, here, and here. Because then I don't have any fractions inside of fractions. And now we're there. Because it's going to be x times 144, that's 12 squared, over x to the 4th, minus 18 is 0. And so we have 144 over x to the 3rd. So these surface area questions tend to have a bit of fraction work. How do we solve that? I find equations like this tend to cause us some trouble. What would you do next? I think some people would add the 18 to both sides, that's fine. But whenever I encounter an equation that has a fraction, I multiply it. I kind of use this over and over again. I multiply everything on both sides. That gets rid of my fraction. And now we've made it. So 144 is equal to 18x cubed. X cubed equals 144 over 18. Oh, that simplifies, but. So if the setup is good, that's kind of the most important part. There's just a little more fraction work in the solving. Does that make sense? Did we answer your question? Yeah. Anybody online have any particular questions?
I don't have a question about this particular problem, but I do have one about reversing when there's time for that.
Yeah, let's do it. Do you have a particular one?
Yeah, it was one of the ones that we were doing earlier. I think I'm missing something conceptually because so it was the one with bounds from 64 to 0 and then 4 to the
That was
y
the
to
e to
130.
the x to the 4th.
Yeah, that one from the homework.
So it looked like integral from 0 to 64. Zoom in a little bit. Okay, so we had the integral from 0 to 64. We had the cube root of y to 4, or was it 2? I can't remember.
To 4, yeah.
And it was 6ex to the 4th dx dy.
Yes. So I was able to draw the picture, like exactly how you drew it. But then when it actually came to putting in the bounds, I got that wrong, and I'm not sure what I'm misunderstanding. So I thought it was 0 to or 64 to 0, which is a red flag because that's the same bound as before. And then I thought it was for the second bound, a is equal to 4, and then b is equal to x cubed.
So let's talk about right. So the outer bounds of the new one are the biggest and smallest values you could plug in for x. So it's kind of like if you were to sweep across here, it's when you're in this region, then you're out again. So when we're looking for that, we're looking for these values. So this is like the A or the start. This is the end. That's what goes in these two spots.
Will it ever be the biggest and smallest like y can be, or is that?
That would only be, so in general, it'll be the biggest and smallest of whatever variable you have here. So this is the biggest y, this is the smallest y. And this is the biggest y. And this is going to be the biggest x and the smallest x. So big picture, you don't really have to know that much about the functions. If you have just a blob, and the blob is between y equals, I don't know, 3 and 7, and it's between x equals 1 and 10, then we already know the outer bounds. So if you're doing it with respect to x, it's going to be 1 to 10 dx. That'll be on the outside. If you're doing it with respect to y, it's going to be 3 to 7. That'll be on the outside. So the good news is that part can be done just by kind of sweeping your hand across the region. So in terms of x or in terms of y. The real pattern finding is finding a pattern based off of an x. So it's, if I say I'm going to hand you an x value between 1 and 10, then your job is to find the patterns for how far to go. Or if I give you a y value between 7 and 3, you have to find. So that's where the work comes in. So in this case, if I'm doing it in terms of x, the biggest and smallest x can be, that required some solving, but this was 4. So you had to figure out when x cubed was 64. And this is 4. But the challenge was to describe where these two things are, the top and bottom. So a couple things. So the correct answer here we need is 0 to x cubed of 6x to the, it's e x to the 4th. If we did the following, sometimes it's helpful to do this. If it had been x cubed to 64, that's a different region. But that would be this region. So let me move this down. That would be this region. This is this region. So sometimes it's good to look at both, to look at these and compare. So for this one, as you walk up, the first thing you encounter is x cubed. That's what that distance is. And then if you keep walking, the last thing you encounter is y equals 64. Whereas in this region, the first thing you encounter is y equals 0, and the last thing you encounter is x cubed. I don't know if that helps at all.
Okay, I think I'm confusing like the regions in which we're using, because I was looking at the wrong thing, I guess, with like the second bound. I thought it was 4 to x cubed because I was looking from left to right. Like the first thing is
Ah,
yeah.
right,
So
yeah.
how do I
One comment about that is you could pick a random number from here, like a 1, and substitute in for your bounds and make sure the appropriate thing is bigger. So, meaning if somebody had set this one up the wrong way and they did 64 to x cubed, that's something that we can catch because if we've done it correct, we're finding a pattern for how far to go based off of x. So you could say, well, what if x is 1? And you grab x equals 1 from the outer bounds and plug it in here. Well, then this would say 64 to 1. And that would kind of clue me in that something's wrong. So this point, it's good to, ultimately we're doing some labeling. Let me say a few things here. So what we're really doing is pattern finding. So if I said x was 0 or 1 or 2 or 3 or 4, we're trying to say how far would you need to walk to be in the region. So whatever formula we think we get, we can test it out. So if we thought the answer was x cubed is less than y is less than 64, and we plugged in 0 to that pattern, we'd get 0 to 64, and we'd say something is wrong because if I stand here, it shouldn't go all the way up to 64 if I'm in this region. So something is wrong with that pattern. It's correct if we write 0 to x cubed, because if I plug in 0, I'm going to get 0 to 0, which is just that 1 point. If I plug in 4, I'm going to get 0 to 4 cubed, which is 64, which is describing what's happening right here when x is 4. If I plug in a 1, it's going to be 0 to 1, which is describing what's happening right here, 0 to 1. It's going to be 0 to 8 when I'm in the middle, 0 to 8. So we're effectively labeling this entire region here. That's what this is doing. So then this would be 0 to 27. We're saying that's the same no matter where you are. 0 to x cubed. Anyways, other questions? Yeah, let's look. I think we've hit. I don't have as many volume examples because there's really just kind of that one. I mean, there are other types of problems, but among the things you've seen, it's really that last question. Let me look here. Already clicked through that one. Partial derivatives, find and classify critical points, set up the bounds for a region. So yeah, this is the one, but we did that one today. Let me see here. Okay.
It's probably like storage.
So you don't have to find the normal vector, but you might have to find these two components of acceleration. So I think of 13.4 as mostly being about acceleration. So let's go, here's a typical question. So one we kind of mentioned today of the integrating. So I was trying to answer one question about that. Here's another one that has to do with acceleration, a 13.4 question. It says, consider the position function given by this. I feel like I did that. Let me give another one because I've done that one a couple times. Maybe this one.
Yeah, I think the,
Yeah, so but the part that asks, so this is where you have to have this formula, the tangential component of acceleration or the normal component are these compute away. We unfortunately don't get to do as much as one might want to in terms of interpreting. The tangential component is the derivative of the speed, so it kind of tells you when the thing has stopped speeding up or slowing down. So usually this is significant, when this is zero. The normal component has to do with curvature and how fast you're going. Based off of the exam space, I'm a little limited in what I can ask. It's got to be computationally feasible. Across the general formulas for the cross product in the the tangential normal component can be pretty big. Because if I say just do it at zero, that makes it a lot easier. If you have to do it in general, you'd have to do a cross product with t's floating around. So that's what I mean. I'm kind of limited. So often the two questions I ask is, compute this and find when it's equal to zero. That was kind of an interesting application piece, or just plug in a number. So yeah, a question like this is really about computing the derivatives. So probably the hardest part of this question is you had to remember what the derivative of arctangent was. So you had 1, 2 over 1 plus t squared, 3 plus. So I had to do some derivative work there. And I need the second derivative. So this was probably the hardest part of this. This is a particularly challenge. Now, in the end, this question is just asking you to plug in a number. But I think the challenge for students here was derivative work. Not the, and, oh, yeah, it is of the inverse trig functions, it's the one that comes up the most. So having this derivative somewhere in our head in the corresponding integral are of use. I mean, we'll see it again, and I think it comes up in a problem in the last 2 weeks, so it's worth just having at the ready. This problem was one where I think, like I said, hard for me to ask questions on this one. This one ended up being more just a derivative practice. So you had a product rule here. First times derivative of the first times the second plus the first times derivative of the second. So I think you get this. Okay, the moment you've written down the derivative, the rest of the question is fairly quick because it's asking you to plug in zero. So if you plug in zero everywhere, you get the first derivative is 1, 2, 3. And the second derivative is 0, 0, 2. And so it was a kind of a boring question then, because then you do the dot product of those two things, which is 6. So the tangential component is 6 divided by the length of your first derivative divided by the speed. So that's just more of a straight, do you know the formula? The other types of questions I've sometimes asked. Let's see if I can find. Find the position vector function, find all values of t at which the tangential component of acceleration is 0. So this is a little more interesting and a little more straightforward than the last one in terms of derivatives. But you have to find when the dot product is 0. You don't really even need to worry about the denominator, but you do need to know when this is 0. So I think the challenge here was an algebra challenge. And this is one of these where the moment I'm doing algebra, I like to get rid of my negative exponents and write them as fractions. Okay. So there's not a lot of variety for what I can ask there. Good. What else can we do? I remember this one being, is this spring 2018. Oh. So this is a challenge in terms of setting up a double integral. All right, yeah. See ya. Yep, sounds good. Well, let's see, they give me y equals 2x, y equals 4x minus 2, and y equals 1. So no matter how you do this problem, you would need to know where these intersections are. And then you'd have to decide whether we're going to do it in terms of x or in terms of y. I think before I'd even start, I would find all these intersections. This is m1x is 1/2. What about this one? This. So this is 3/4, half. And then one other intersection. So what looks easier in terms of X or in terms of Y? For a second. There's actually one that's quite a bit nicer. And it has to do with the fact that if you draw a line right here, the bottom changes. So I don't really want to do it that way. If I have a choice, I would do it in terms of Y. So one question is, what's the biggest and smallest Y can be? And then based off of that, what are the patterns for X and Y? Did you have any other questions or just kind of listening? So what's the biggest and smallest Y can be? If I walk up this axis, first hit the region right here. So that's the smallest Y. And I'm in the region up until here. That's the largest Y. So that's 1 to 2. And then based off of Y, I need to know the biggest and smallest X can be. So I need X equals something, which is the left, and X equals something else, which is the right. The left is this side. And that corresponds to the equation Y equals 2X. So maybe I can ask what goes here. Well, we need to rearrange. So if I give you a Y, this would be Y over 2. I'm rearranging this. We can test it out. Like if we plug in a 1, we get a half. Plug in a 2, we get a 1. Okay, so I'm going to do the same thing for the upper bound. So let's see, adding 2 to both sides, dividing by 4. And we got it. The other things, I think. Can't remember if that class starts at 1. Did your class start at 1? Okay. So I might have to start